All right, here are the rest of the 3.2 notes. Hopefully this is helpful, and we'll finish it up for you and you understand. If you don't understand something, you can always pause the video, rewind, play it again, and maybe the second time you'll understand it better, or maybe the second time I'll say something different, who knows. But I believe first period we didn't get to the back at all. Third period we got to the top of the back, but we'll go through the whole thing so that everybody sees it again. And this is 3.2. So principles of experimental design, we talked about principles of randomization on the front. Now we are there, principles of experimental design. So the first one, there's three here also. Okay, the first one is to control of lurking variables. The second one, randomization of the experimental units. And then the third part is replication. So if we were to do this experiment over and over and over again, would we get similar results? That's the key there. If we just do it one time with a very small sample and we get results, it might not be such a great idea to generalize those results over a whole population. Kind of like the polls for the presidential thing when they asked 404 people. They really need to do it over and over and over again. So that's those are our three principles of experimental design. Now, statistically significant is an important term. It's kind of like extrapolation and restricted range. It's one of those big statistical words that we want to be able to use in context. And we say something is statistically significant if a difference that is too big to attribute plausibly to chance. Remember we said when we were doing a treatment, we are looking for the response, the change in the response, and we want it to either be because of the treatment or because of chance. Well, if it's statistically significant, we're going to say that it was because of the treatment and not chance. Okay, so that is the principles of experimental design, a little bit on statistically significant. Now, use of a random number table. Okay, now I said in this unit, the only time we'll be using numbers is if it's a Unit 2 or a Unit 1 problem. We are going to use a random digit table. It's the very, very last page in your book. It's two-sided. And you'll notice all the numbers on there are 0 through 9. So there's 10 total digits. Okay, and they range from 0 to 9. And they're random. They don't, if you have 1, 2, 3, you could have 1, 2, 3 again. You could have 4 ones in a row, 5 zeros in a row. They are completely random. So they are independent. That goes right here. Okay, independent of each other. I'm going to write it here. They're independent of each other. So here's how we're going to use this table. If we have, let's say, 30 students in the class, okay, we're going to number the 30 students from 01 to 30. If there are two-digit numbers, so there's 30, so that's two-digit, we have to code everything with two digits. If there are only 8 students, I'll write up here, you could code them from 1 through 8, one digit. But anytime double digits, we have to have two-digit codes for every student. Now, since we are doing doubles here, we're doing pairs of numbers together, we need to look at numbers on the random number table in pairs. So, if I had to pick 5 people randomly to transfer out of this class, who would they be? So I number my students from 01 to 30, and I say look at line 130 on the random number table. So if you flip all the way to the back of your book, the very last page, it's not a regular paper page, it's kind of like a hardstock page. You look on the left side for line 130, and this is what that line would look like. Now, to find the first 5 people, I start from the left, and I look at two-digit codes. So I have 69, but that's not one of my 0 through 30, 01 through 30. But I have 05, that'd be one student. I have 16, that would be another one. 48's a no. I have 17. 87's too big. I have 17 again. I already picked him. 40, 95, 17 again, 84, 53, 40, 64, 89, 87, 20, and 19. So as soon as I have all 5, I can stop. So my numbers of the students, I had 5, 16, 17, 20, and 19. Now, because it's a random number table, I specifically said start on line 130. You may have some homeworks where it tells you to start on a specific line. Others, you can pick wherever you want. Just tell me what line you started with. On the test, it'll look like this, where I will have a list of numbers written out already, and you just have to read it just like I did. Okay. So, when I'm using this random number table, the other thing you have to be careful on how the question is asked. This says enter the table at line 130. Sometimes it may say enter the table from the right at line 130. And if I do that, that's read 54, 27, 91, 2. So be careful how you read the question, English part again. You have to be able to read the question and figure out which way you're going to go. Now, just if you have multiple groupings of experimental units allocated to all treatments, the experiment is said to be completely randomized. So that's like the drawing we did yesterday. So if we had this, we had our subjects, and then the arrow, remember, means completely randomized, and this is group 1, maybe this is the treatment group, and this is group 2, this is the control group. Oh wait, that's Halloween. Trick or treat, get it? And then we compare results. So if you had to diagram a completely randomized experiment, this is what it would look like. Now, a couple of things we have to look for. Okay, cautions. And the cautions are, again, these are one of those things that will show up on the test places, so make sure you know these. First one is hidden bias. Okay, so you have factors that are contributing to they're factors contributing to a specific outcome. And they're hidden, so we really don't know what these factors are. So one of the things we talked about was placebo effect. Okay, another one could be the researchers. So a lot of times we said with drug companies that they get an outside testing to do their results, so they don't feel that, so people don't feel that they're trying to tweak the results to get it to the way they want to look. So one of the ways to lessen hidden bias, okay, is a double-blind experiment. This is important because we're going to need to make sure you know when it needs to be double-blinded, when it doesn't. If we're talking about plants, we don't need the double-blind. But when we're talking about humans, we really need to do a double-blind experiment. Okay, so we can lessen the effect of hidden bias by using a double-blind experiment where neither the subject nor researcher knows who's getting which treatment. So somebody has to know who's getting the treatment to know what group they're in, but maybe the patient doesn't know which drug they're getting, if they're getting the weight loss drug or not, and then maybe the person checking the weight at the end, okay, that person doesn't know who got which one. They just know this is subject number 25, this is subject number 37, okay? And they do the weights, and then they give it to somebody else who tabulates the numbers. So that's double-blind experiment. So we said this means randomization, this arrow right here. And then normally what we do to show blind or double-blind is we put blind right here, and we put 2 lines underneath, and we put arrows above and below, right over here. So double blind, but double blind, and we do it right here where we compare results. So that tells me, or tells us as we do this diagram, that it's a double-blind experiment. My computer went off, so I can't see what I'm doing. Hold on. I think I'm still going. We're good. Okay, now, part of the problems with doing experiments is they lack realism. Okay, so we might not be able to create in a lab or a testing situation what would happen in real life. So laboratory settings are a good example. If you do something in a lab, it's obviously not, no, it's not a real. Sleep tests, those are good ones to say. You don't usually sleep with all these things attached to your head at home. And when they do sleep testing, they usually put sensors all over your head to see what your brain activity is and trying to figure out if there's a reason why you can't sleep. So that's an issue there. Now, down here at the bottom, this is another part. Different ways you can conduct an experiment. Okay, one is called match pairs, where you give two twins the same diet drug and see if one affects, or give two twins. You have two twins in an experiment, give one of them a diet pill, the other one not a diet pill, and see if there's a change between the two because you're using the same one. Another one, you may have seen commercials on this, is the different razors, where they will shave each side of a guy's face with a different razor and then see which one grows back faster. That would be an example of a match pairs test. Blocks, where you put things that are known to be alike together. On the Unit 1, or maybe the Unit 2 review, remember we had a problem where you did a box plot for wide receivers and a box plot for running backs. Well, maybe those two blocks are different, so you block them first into wide receivers and running backs and then do testing on that. And when you do a block, if you block them by category, then we put them into a block design. That's what this thing up here is called, is a block design. So we get our subjects, then we randomly put them into two groups, and we test from there. Okay, so those are the 3.2 notes finished up with. The 3.2 homework is pretty simple. You're just you're basically looking at situations and pulling out the factors and the treatments and the levels of factors like we talked about on the front. And there's one problem on the back that you have to use the table of random values. It's the one with the 4x4 square with the bugs. But that should be it. On Friday, we're going to do a test problem to see kind of an in-class little quiz, not a quiz problem, but a little test problem to see if you knew how to do it. So, but we'll go over this again Friday in class. Hope it helps.